In mathematics, it's often the simplest shapes that hide the most profound ideas. And today, we're exploring Hadamard's three circles theorem. It sounds like it's just about geometry, right? But it actually holds a key to one of the deepest unsolved problems in all of math. So it all really boils down to this one question. How can something as basic as three circles on a page have anything to do with the legendary Riemann hypothesis? We're talking about one of the $1 million Millennium Prize problems here. Well, stick around because we're about to connect those dots. So here's our game plan. First, we'll see exactly why this theorem matters for Riemann. Then, we're going to build the three-circle setup from the ground up. After that, we'll reveal the core inequality, the heart of the theorem, and break down what that formula really means. And finally, we'll get to the powerful payoff this whole idea delivers. Okay, so why should any of us care about three circles? Before we dive headfirst into the geometry and the formulas, let's start with the big picture. Because understanding its connection to such a legendary problem, well, that's what gives this theorem its real power. Now, let's be clear. The theorem itself doesn't solve the Riemann hypothesis. But what it does do is provide a vital tool for mathematicians to probe its consequences. In fact, it was famously used by the mathematician J.E. Littlewood to make a really profound connection, which we'll get to at the very end. All right, to really get to the heart of this theorem, we first need to build the world it lives in. It's a very visual, very geometric idea, so let's set the stage. Everything, and I mean everything, happens inside this shape right here. It's called an annulus. It's really just a fancy word for that flat, donut-like region you get between two circles that share the same center. Think of it as our mathematical arena for today. So let's define our circles inside this arena. We start with the outer circle. It has a radius we'll just call R3. Now imagine some function living on this plane. On this outer circle, the function's value hits its absolute peak, and we'll label that peak M3. Next, we draw our inner circle with radius R1, and same deal, its maximum value is M1. The whole goal of this theorem is to figure out what we can say about the maximum value, M2, on that middle circle that we can place anywhere in between. And that question brings us right to the climax of the theorem. We have our setup, we have our goal, so now let's see the mathematical statement that ties this whole thing together. Okay, if you actually look at the original derivation in the source text, you see this. It looks pretty dense, doesn't it? Logarithms everywhere. This is really the machinery under the hood, showing how the result is all put together. But don't worry, the beauty of mathematics is that this kind of complexity often simplifies into something truly elegant. And here it is. All of that dense text boils down to this single, powerful inequality. This right here is the heart of the three circles theorem. It states that M2 raised to the power of log R3 over R1 is less than or equal to M1 raised to the log of R3 over R2 times M3 raised to the log of R2 over R1. It's a mouthful, but it basically connects the maximum on that middle circle to the other two using their radii to create these really interesting exponents. I know, that's a whole lot of symbols, so let's unpack what they actually represent. Because once we define the terms, the intuition behind the formula becomes so much clearer. And what's great is how simple the components really are. The r's, they're just the radii, the distances from the center to the edge of our three circles. And the m's, they're just the highest peak the function reaches on each of those circles. That's really all there is to it. We can simplify the notation even further into this super compact form. M2 is less than or equal to M1 to the power of alpha times M3 to the power of beta. Here, those Greek letters, alpha and beta, are just placeholders for those logarithm terms we saw a second ago. You can think of them as weights. Their value changes depending on how close that middle circle is to the inner one or the outer one. So what is this formula really telling us? Well, it means that the maximum value on the middle circle, M2, is bounded by a special kind of average of M1 and M3. It's called a weighted geometric mean. To put it simply, the peak of the function on that middle circle can't just be whatever it wants. It's strictly held in check by the peaks on the circles that surround it. And that brings us to the payoff. We've built the theorem, we understand the formula, so now let's connect it all the way back to that million-dollar question we started with. This right here is the crucial leap, and it was made by J.E. Littlewood. Using the three circles theorem as his main tool, he proved that if the Riemann hypothesis is true, then another really important idea, the Lindelof hypothesis, must also be true. This was a massive discovery. And hey, you don't have to take my word for it. Here it is, right in the source material. It explicitly says that Littlewood proved this connection as a simple application of this theorem. That's a direct testament to the incredible power hidden inside those three simple circles. So what we have is this powerful logical chain. Hadamard's theorem about circles gives us the tool. Littlewood uses that tool to build a proof, and that proof reveals a profound consequence of the Riemann hypothesis. It's just a perfect example of how one area of math can unlock secrets in a completely different one. So we're left with this pretty amazing thought. A simple geometric idea about circles became a key to probing one of the most abstract and difficult problems in number theory. It really makes you wonder, what other elegant connections like this are just hiding in plain sight, waiting for us to discover them?